In this section, we're going to talk about the Chi-Square test of independence. This is a very useful test that my students often say they have to use in other classes. So pay attention. So let's recall when we talked about conditional probabilities, I have this table where you can see people broken down by their gender and also which job they had at this university. And I wanted to know if being male affected your chances of being faculty. So I want to know if it was a little biased towards the males. And we answer this using conditional probabilities, but we can actually do an official hypothesis test to answer this. So again, we wanted to know if your gender affects which job you get. So we're asking if gender and job are independent or dependent. To refresh your memory, independent means gender and job do not affect each other. Dependent means gender and job do affect each other. So what we're going to do is we're going to actually compare the actual number of people in each, I call this job cross gender cell. So each cell, like 1, 2, 3, 4, 5, 6. We're going to compare all of these actual data values to the expected number of people in each cell if the gender and job were independent. And we say if they're independent because that's kind of our status quo and is also what we know how to find probabilities for. Now our observed or actual data is easy to find. They're just on the table. But how do we find the expected counts? So what I'm going to do is I'm going to make a separate table with expected counts, but I have to go through and actually find them. So these are my observed counts, or our actual data, and this is my expected, if the variables really are independent. So to find the expected counts, we say, well, if A and B are independent, then remember from our probability lessons, then the probability of A and B will be equal to the probability of A times the probability of B. So our first cell is male and faculty right here. And we're going to make our null hypothesis that our two events are independent, that they do not affect each other. That's a good status quo, right? So if the two events are independent, then the probability of male and faculty would be equal to the probability of male times the probability of faculty. And I can actually find these probabilities by saying, okay, probability of male, let's see, there were 200 males out of 300 people total. So probability of males is 200 out of 300. And probability of faculty, let's see, there's 120 faculty total out of a total of 300. So that would be my theoretical probability, and I'm not going to simplify that at the moment. I have a reason why. Let's see, so that would be the probability. So if we want the expected number of male faculty members, we need to multiply our total sample size by the theoretical probability of that cell. So our total sample size overall is 300. So we're going to have 300 times this probability we just found, which is 200 over 300 times 120 out of 300. Notice what happens here. We get to cancel one of these 300s. That's not coincidence. That's going to happen every single time. So we have left 200 times 120 over 300. And we can write this as a general formula. This 200, notice the 200 was our column total, and the 120 was our row total, and 300 was our overall or grand total. So we're going to write this as a nice little formula that it's our column total times our row total over our overall total. So if we do that, we can go through and we can find the expected value for every single cell. So in our case, 200 times 120 divided by 300 means that this expected count was 80. So I can go back up to my table and say we would expect 80 faculty members, but we actually had 120. Okay, so I could go through and I can use my formula to find out all of these values, which we'll do in a couple pages after we learn a little bit more theory. But we want to compare our observed values to our expected values. So one of the ways we might do this is we might subtract our observed value and our expected value. But then depending on what scale you're talking about, if you're talking about a really small university, a difference of 10 might be a big deal. If you're talking about a really huge university, you might need a difference of like 1,000 to be a big deal. So we might want to scale it based on how big our sample size is, or in some way. So what we actually do to compare our observed and expected counts, we'll use a Pearson Chi-Square test statistic. So you have this little X-looking thing that's a little bit fancy. This is our Greek chi. So we always call it chi squared. And it's the sum of, we're going to do each cell, we're going to do the observed count minus expected count. And then we're going to square them so positives and negatives don't cancel each other out. And divide by the expected counts to scale it kind of for the size of the university. Now, if gender and job are independent, what values of chi-squared would we be expecting? Well, if they're independent, we calculated all of those expected values, assuming that they're independent. And so if they really are, the observed and expected should be the same. They should be close to the expected values because all of those expecteds were calculated with the assumption that they're independent. So if they're about the same, we should be getting pretty small differences here. So we'd be expecting small values of chi-squared. But if gender and job are dependent, then all of those expected values are going to be way off, and we would expect to get big differences. So we'd expect big values of chi-squared. So our chi-square test for independence, we use this if we have what's called that contingency table with two variables, where we had variables going down and variables going across. And we want to know if the two variables affect each other. Sometimes we say, is there a relationship? And we only have one sample from one population. This is more if we get more complicated and compare it to several other kinds of chi-square tests. You won't really need to worry about that too much. The assumptions is all the expected cell counts are at least 5. If you don't have a big enough sample size, you can't use this test. The null hypothesis is the two variables are independent. So again, status quo would be that they don't affect each other, so null is always that the two variables are independent, or that there's no relationship between them. The alternative is the two variables are dependent, or there is a relationship. To find each expected cell count, you'll do the row total times column total divided by total sample size, or overall total. Our chi-square test statistic is the sum of all of the cells, and we'll do each observed count minus expected count squared over the expected count. Our degrees of freedom is r minus 1 times c minus 1. This is r means the number of rows, so it's number of rows minus 1 times number of columns minus 1. And it's very important here that you don't count the totals. The totals don't count when you're calculating degrees of freedom. And the p-value, so because we said if gender and job are dependent, we'd expect big values of chi-square. We're always looking for big values of chi-square, so we only look for the area in the right, so it's a right tail test. So let's try this out for our data. Again, here's our job and gender. We have all of our observed counts, and now I want to fill out a separate table with the expected counts. So remember, we already found males is 80. Now I need to do this for all of the rest, which kind of takes a while. So this is the only time where I actually have you do some work before you start doing like alpha, or saying what your level of significance is, and your hypotheses and things. It's easiest to find your expected counts first. In case they're too small and you say, I just can't do this test. So expected counts are row total times column total over your grand total. So let's try to get a few of these. So let's try maybe female and faculty. So faculty and female would be this spot here. So our row total is 120, our column total is 100, and the overall total is 300. This gives me 40. So we'd expect 40 female faculty if the gender and jobs were completely independent. Okay, let's try maybe this spot for salaried staff and males. So males and salaried staff. Looks like our row total is 80, our column total is 200, and our grand total is 300. This gives me 53.3. So we'd expect 53.3 males that are salaried staff. Let's try maybe this bottom one here for females and hourly staff. So 100 as the row total, 100 times the column total, divided by 300, gives me 33.3. This is 33.3. So continue doing that for every spot, and you're going to get 26.7 and 66.7. Now, here's what I like about this. Check your totals. Do 80 plus 40, that's 120. 53.3 plus 26.7 is 80. 66.7 plus 33.3 is 100. Add up all of these numbers for the column and you get 200. And add these up for this column, you get 100. And if you add up the rows or add up the columns, either way you get 300. So your totals shouldn't change. So your observed and expected totals will always match. This means two things. One, it means you can double check your work. Or, if you want to save a little bit of time, some people have noticed, if I fill out like this 80 and 53.3 and I know what my totals are, I can get all the rest by subtraction. So like 120 minus 80 would give me 40. Or 200 minus 53.3 and 80 would give me 66.7. So you can save yourself some work just using subtraction and get all of these numbers in here if you know what your totals should be. I prefer to double check my work instead, but you can do that. And so it's interesting to note how many cells do you actually have to find this way before you could just use the totals. And you only have to find 2. And it turns out later that our degrees of freedom is 2. And that's how degrees of freedom actually relates. Is how many cells could kind of like change before, or do you have to find before the rest are all set based on the totals. Now that I've found all of my expected counts, we can actually start our test. So I'm going to choose alpha equals 0.01, just because I think it'd be pretty serious to accuse this university of bias if it's not actually true. So I'm going to set it pretty small. I don't want to accuse them of bias if it's not true. Let's check our assumptions, which is that all expected counts are at least 5. Let's see, 80, 40, 53, etc. Those are all pretty big. So we're good there. We need our null and alternative hypotheses. The null is always that they are independent. So gender and job are independent. And because sometimes you have trouble remembering which one's which, I like to always write it out. That means they do not affect each other. Because that's what I really want to make sure I tell my boss, in case he doesn't know the difference. And gender and job are dependent, meaning they do affect each other. Then the next step is always find a test statistic. Chi-squared, our test statistic, is equal to each observed minus expected value squared over the expected. This is what takes quite a bit of time to do. So I go through and I say, okay, my first observed value is 110. And then I match it up to the expected value in the same spot, which is 80. Square it and divide by 80. Plus, and then I go to my next one, which is 10, and match it up to its expected of 40. So 10 minus 40 squared over 40. And I'm going to do that for every spot. It doesn't matter what order I have them in, as long as I match up the correct cells. So 30 and 53.3. 30 minus 53.3 squared over 53.3. Now the things I see people mess up on the most is they accidentally divide by the observed value, or they don't make sure they match up their cells correctly. And then 50 and 26.7. and 60 and 66.7. And finally 40 and 33.3. After you've done all this, which I admit takes a long time, we get chi-squared equals 66.3. Now you also need degrees of freedom, which is r minus 1 times c minus 1. This means number of rows minus 1 and number of columns minus 1. Remember, we don't count our totals. So how many rows do you have? It looks like you have 1, 2, 3 rows and 2 columns. Make a note, 3 rows, 2 columns. We don't count the totals. So 3 rows minus 1, 2 columns minus 1 gives me 2. Again, remember we had 2 cells that, if you will, could kind of vary and then I could find the rest just by using our totals. Our p-value, here's our chi-square test statistic of 66.3. And remember, we always want the area to the right. So we need to pull up our chi-square table. Make sure you use the chi-square table that has areas to the right. We want the right one. And we had 2 degrees of freedom, and we're looking for the number 66.3, which is going to be somewhere way, way, way off here. So my p-value is less than 0.0005. Really, I think it's probably going to be very close to 0 because that's such a huge chi-square test statistic. And in fact, if you use the computer, you can find the exact p-value is 4.03 times 10 to the negative 15. So that's an incredibly small p-value. So that is a small p-value, so we'll reject the null hypothesis. And because we reject the null, we have evidence for the alternative, so evidence that job and gender are dependent. Remember, dependent means that they affect each other. So my final conclusion will be something like, we have extremely strong evidence that gender affects the job type. Now you might notice here that I'm saying gender affects the job type. The test itself only tells you that there is a relationship, that they kind of affect each other. It doesn't say which one kind of affects the other one, but you can think about this logically. If you have gender and job type that are affecting each other, it would have to be that your gender affects your job type, because people aren't going to change their gender after they get the job to be a faculty or to be salaried staff. And so it must be genders affecting job type. So one more example, does subscribing to Beacon News affect whether you subscribe to the Atlantic Journal? So we have Beacon News and not Beacon News, Atlantic Journal and not Atlantic Journal, and we want to know if they affect each other or not. So first step is find the expected counts, which our expected counts are row total times column total over overall total. So let's find this spot right here. So for Beacon News and Atlantic Journal, we'd have 650 times 500 divided by our grand total of 1,000, which is equal to 325. And then let's maybe find this spot. So we have our totals of 350 and 500. So for not Beacon News and not Atlantic Journal, we get 350 times 500 over 1,000, which is 175. Now you need to do all of the spots, but you can go ahead and do that on your own instead of my taking time to do it all. Now you'll notice here I didn't actually put in 2 different tables. Sometimes I like to save space, or if I'm doing this by hand, I really don't want to draw out 2 tables. So the one that's typewritten in, these are obviously my observed counts, and then I'm just going to write the expected counts next to it. So this was 325 and 175, and I just know that the ones that I write in are the expected counts. And then this is also 325, and this is 175. Double check that your totals are still the same. That's a good way to double check your work. For our actual hypothesis test, we have alpha equals 0.05. Let's check our assumption, or if you will, our requirement to do this test is that all the expected values are at least 5. Well, the smallest is 175, so we're definitely good there. Now, if you came across a situation where you had an assumption that was less than 5, you'd say, okay, I can't do this test. I would have to do a different test that we haven't actually learned about. For our null hypothesis, it's always that they're independent, so reading or not reading the Beacon News and reading or not reading the Atlantic Journal are independent, meaning they do not affect each other. The alternative hypothesis then is that they are dependent. They do affect each other. Then you need your test statistic, which is chi-squared. Which is equal to each observed value minus the expected value squared over the expected. This is why I kind of like doing the same table, because it's really easy to see which ones go together. So we'll have 250 and 325. So 250 minus 325 squared over 325. Plus my next cell, I'm going to do 400 and 325 squared over 325. And 250 minus 175 squared over 175. Plus, my last one is 100 and 175. 100 minus 175 squared over 175. Which gives me 98.9. That's a huge chi-squared value as well. Degrees of freedom is r minus 1 times c minus 1. So remember, number of rows and number of columns is what those stand for. So this one looks like it has 2 rows and 2 columns. We don't count the actual total rows and columns. So we have 2 minus 1 times 2 minus 1, which just gives me 1. For my p-value, here's my chi-square test statistic of 98.9, and I want the area to the right with 1 degree of freedom now. So 1 degree of freedom, 99 is going to be somewhere way, way, way out there. That's a very, very, very small p-value. P-value is less than 0.0005, but really very close to 0. My computer could tell me what the exact value was. But it's definitely small, so we'll reject our null, because it was a small p-value. And if we reject our null, that means we have evidence that they are dependent, or meaning they affect each other. So we have evidence, well really that was a very small p-value, so we have extremely strong evidence that subscriptions to the Atlantic Journal and Beacon News affect each other. Now this is one where they probably both affect each other, really. If you like to read one journal, you're more likely to get more than one journal. And there's probably not, if you read the Atlantic Journal, then you automatically read the Beacon News. It's probably not a one-way street. It's probably going both ways. So we'll just leave it